Now let's consider the entropy. Now, when we discussed the enthalpy in the first semester of freshman chemistry, you learned that it was a state function. And a state function depends only on the initial and final state of the system. It is independent upon the path between initial and final states. So a state function is path independent and only depends on where you start and stop when you perform a process. Now when we look at, say, a particular thermodynamic process, we find that a state function exists if we look at the heat flow divided by the temperature for the total process. And then that is given the definition of entropy, where S is given the symbol entropy. And I've used calculus language because this is thermodynamics, is the change in the heat flow. So we're looking at heat flow, which is change. So I use the change in the entropy here is equal to the heat flow divided by the temperature which that heat flow occurs. We can integrate both sides of the equation, and since the entropy is a state function, it only depends upon the initial and final states, or starting and stopping. And then we'll have the integral of the heat flow divided by the temperature. So this is the definition of entropy in an algebraic sense. The key to determining the entropy is representing the heat flow, dq. So in order to calculate the entropy, we have to represent the heat flow, dq. And one of the simplest examples we found in the first semester as well is the heat flow is equal to what we call a heat capacity, it's a constant, times the temperature change. And if we integrate both sides of this equation, we will get our common expression for the heat flow is equal to the mass times the specific heat times the change in the temperature. So this is how we can express the heat flow. So going back into our entropy equation, dq is equal to c dt, and if we integrate both sides, we will get delta S is the integral of the heat capacity times the change in temperature divided by T. And if the heat capacity is a constant, we can take it out of the integral, and then we'll have just delta S is the heat capacity times the natural log of the final temperature divided by the initial temperature, or the temperature for state 2, which I say is final, and the temperature of state 1, which is the initial. This is how we can express the entropy change when we have a change in temperature due to heat flow. There are two ways that the heat flow can occur. It can occur through a process of constant volume or constant pressure. And if we have constant volume, we use the heat capacity at constant volume. And if we have constant pressure, we use the heat capacity at constant pressure. And for an ideal gas, these two are related by the factor R, the ideal gas constant. Now we can say the entropy change for heating at constant volume is equal to CV times the natural log of the ratio of the temperature final over temperature initial. So this is at constant volume process, or we can say the entropy change for a constant pressure process is the heat capacity at constant pressure times the natural log of the quotient of the final and initial temperatures. So this is under condition of constant pressure. So these two equations are important. We use some calculus language and a couple of integrations, but you don't need to reproduce that. Just need to know these two equations and using them under constant volume or constant pressure conditions. And you'll be told whether you have constant volume or constant pressure. Now you can look up the heat capacity at constant pressure in common tables, like in any freshman chemistry book. And you can get CV, because CV is CP minus R. So if you have CP from a table, you can get the heat capacity at constant volume just by subtracting R in the ideal gas approximation.